Assalamualaikum. My name is Husna Izzati binti Sani with the matrix DN180070. So the title of my project is Development of Bilayer Transdermal Wound Healing Patch loaded with Bromelain under the supervisor of Dr. Nadir Hasraf bin Manayan. So next we go to the introduction. Wound healing is a complex mechanism that includes the activation of fibroblasts, endothelial cells, and micropatch to restore impact cells and tissues to their normal state. Management of chronic wounds involves the use of antibiotics, anti-inflammatory agents, or combination of both, but some of these drugs are associated with unwanted side effects, hence the need for other alternatives without producing toxicity. Wound dressings plays critical roles in wound treatments, and either wound dressing should protect the wound from external contaminants and facilitate the healing process. However, most of the wound dressing have been produced only with one layer of the polymer, causes a tendency of contamination and slowing down the healing process due to its low properties. Recently, composite has been selected by many researchers to produce the best wound dressing for wound healing. Composite dressing are convenient for both partial and full thickness wounds. The composite dressing is made up of multiple layers, and each layer is biologically distinct. The selection of material in wound healing is a crucial process for scaffold, which PVDF and PVA are selected to develop an electrospun nanofiber layer, while PVA, collagen, and HNT are used to develop hydrogel structure. The bilayer composite layer will be loaded with Bromelain for wound healing improvement. So the objective for this study are first, to develop a transdermal bilayer wound healing patch in a combination with the electrospun hydrogel scaffold. Second, to characterize the properties and structure of composite. Next, to evaluate the percentage of trap loading in composites with Bromelain solution as a model trap. So next we go to the literature review. PVDF, a piezoelectric polymer, is widely used in tissue engineering because of its ability to imitate the electrical microenvironment to biological tissue development. However, PVDF has a poor reactive side exchange with hydrophobic properties, which can promote inflammation in the host cell or tissues. For that reason, some modification and enhancements for those specific properties are theoretically necessary. PVA is a non-toxic biodegradable synthetic polymer that possesses hydrophilic properties, consists of a backbone that comprises the carbon atom and pendant of hydroxyl group. PVA was introduced into electrospun PVDF application through an electrospinning process to enhance the nanofibrous membrane's biocompatibility properties by improving the hydrophilicity properties. Electrospinning technology has evolved to the point where synthetic or natural polymers can be used to generate modified ultrafine nanofiber. By utilizing the electrospinning method, nanofibers become a promising strategy in the treatment for the wounds. So next, for the hydrogel are made up of natural or synthetic polymers with or without non-polymer particles. This 3D cross-linked or interconnected polymeric network of fiber within the fluid system form a sol-gel formless structure. For natural collagen is frequently used for surgical repair due to its low antigenicity and inherent biocompatibility with most endogenous tissues. HNT, or sometimes can be referred to as non-oxidized triple halosite, is an aluminosilicate with a multi-layer tubular structure of a 1-1 km layer. Multiple researchers reported that HNT can act as a reinforcement for the nanocomposite scaffold, which will directly result in the enhancement of the mechanical properties of the nanocomposite. So for Bromelain, Bromelain is a pineapple extract found in all sections, which has a high concentration of proteolytic enzyme. The Bromelain, which acts like a trap in electrospun, is proven to remove burn debris as well as speed up the healing process. So Bromelain has been chosen as the enzyme in the composite for trap loading testing. The concentration of Bromelain in this testing is 200 mg and 400 mg respectively. From the experiment, it can be observed that the low concentration of Bromelain has a potency of high trap loading. So next we go to the methodology. First, the preparation of PVDF PVA electrospinning layer 9010. So the fabrication of PVDF PVA electrospin layer will be prepared at PVDF to PVA ratio of 9010. The PVDF polymer solution will be dissolved in dimethyl sulfoxide solution at 50 Celsius with magnetic stirring and followed by dissolving PVA at 90 Celsius until clear polymer solution form. The polymer solution will be mixed, resulting in a homogeneous PVDF PVA polymer solution. The copolymer fluid will be injected into a 5 ml disposable plastic shrink using a 20 gauge needle. The shrink will be loaded into an electrospinning unit with a horizontal setup that deliver the polymer to a cold panel. So next is the preparation of bilayer composite. PVA and collagen will be mixed using PVA to collagen ratio at 90:10 in distilled water at 90 Celsius, forming a 50% concentration solution. Then 5% of HNT will be added into the PVA collagen polymer solution by stirring for 30 minutes until composite solution fully homogenized. The electrospin will be placed in the mold at the bottom layer. Then PVA collagen HNT polymer solution will be poured onto the electrospin layer in the same mold. The sample will be in a freeze thaw process at -20 Celsius and 23 Celsius for 3 cycles in 24 hours. So next is the field emission scanning electron microscope, FISM. So the surface morphological, cross-sectional mesh and elements of composite were examined by FISM. The samples taken from each member were coded using a Catan precision etching coating system, PECS. And then mechanical properties. Tensile strength and Young modulus for film samples were obtained with a metal tester at room temperature 22 Celsius using a 5.6 Newton load cells, 21 mm per min preload stress speed and extension rate of 10 mm per min. Sample of different composite was cut into rectangular shapes with a couch length of 50 mm and width of 10 mm. The sample were clamped and subjected to tension until breakage. So the last one is drug loading testing. So the model drugs of Bromelain were loaded into different composite using post-loading method. The samples of composite was immersed in 200 mg and 400 mg saturated model drug solution at 32 Celsius and 1 hour were optimum conditions to ensure maximum drug load. So the drug composite was then weighed and the drug load was determined by using equation. So next, we go to the result and discussion part. So for the first set, this image shows the cross-sectional composite of electrospin, hydrogel and bilayer composite. The structure of electrospin are observed as discrete and fine fibers. The average fiber diameter of electrospin nanofibers is 100 to 500 nanometer. The image revealed that there is bit formation on the nanofibers. As seen in the enlarged SEM image, the hydrogels exhibited homogeneous distribution and interconnected porous structure with no significant phase separation observed. Cross-section image of bilayer composite in the combination of electrospin with hydrogel shows the two-layer structure, which the first layer is electrospin nanofiber and the second layer is a hydrogel. It can be seen that hydrogel incorporates well with the nanofiber where there is no gap between them. As a combination of electrospinning and hydrogel, bilayer composite has a three-dimensional structure that provides a suitable microenvironment allowing cells to submerge and develop, as well as a three-dimensional structure for wound healing. So next, for the EDX, the element analysis of the cross-section of composite electrospin, hydrogel and bilayer composite was carried out using the energy dispersive X-ray spectroscopy instrument. The characterization of element composition in electrospin reveal the presence of carbon, oxygen, sodium, magnesium, iodine, fluoride, chloride, calcium, and aluminium. It was observed that the carbon is the highest consumption in the nanofiber yield to 60.40% and followed with fluoride, which is 36.07%. The element present in a hydrogel is a carbon, oxygen, sodium, magnesium, silica, niobium, and plumbum. So the percentage of niobium and carbon is 67.56% and 18.22%, being the highest consumption in the hydrogel. So when the electrospoon and hydrogel were combined as bilayer composite, several elements show a percentage increase in the composite, including carbon 80.56%, oxygen 60%, sodium 80.56%, magnesium 0.53%, chlorine 1.114%, and calcium 0.58%. The increasing of the component in the bilayer composite demonstrates the strong interaction between them that provides benefit in wound healing application. So next, for the mechanical analysis, the result shows that the incorporation of electrospoon and hydrogel has contributed to the addition of mechanical properties in bilayer composite. As compared to electrospoon and hydrogel, the tear index of bilayer composite increased by 55.80% and 10.48%, and for the burst index of bilayer composite increased by 49.89% and 20.64%. For the tensile strength of bilayer composite increased by 81.15% and 56.81%, while the Young modulus remarkably increased by 82.10% and 72.60%. So for the last one is the percentage strength of bilayer composite also increased by 70.97% for electrospoon and 2.92% for hydrogel to 46.25%. So overall, the bilayer composite mechanical properties meet the requirement for tissues application in wound healing at the scale for tear index, burst index, tensile strength, Young modulus, and percentage strain of weight. So for the last one is drug loading. It was observed that electrospoon achieved a lower percentage of drug loading in both concentrations of bromelain. Due to the structure of electrospoon mentioned above as discrete and one-layer composite, the lower absorption ability of the drug has been obtained. This is followed by hydrogel, which has a high percentage of drug loading, which is 68% for 200 mg and 70% for 400 mg. The presence of hydrogel as a gel structure gives the strong absorption ability of the drug that achieve a high percentage of drug loading. As a combination of electrospoon and hydrogel, the bilayer composite matrix with 200 mg and 400 mg of bromelain yield a higher percentage of drug loading, which is 75% and 78%. So, bilayer composite also has a higher absorption ability of the drug that gives a high percentage in drug loading. Therefore, this can be attributed to the low concentration of bromelain having a high capacity in drug loading, which drug loading has flexible properties that enable to increase the percentage in any concentration of bromelain. So next, for the conclusion, so the development of bilayer transdermal wound healing patch loaded with bromelain has been successfully achieved. Bilayer composite shows a two-layer structure that provides a suitable microenvironment, allowing cells to submerge and develop in wound healing application. EDX image describes the presence of component and percentage increase of element in bilayer composite. So next, the bilayer composite mechanical properties meet the requirement for tissue application in wound healing, offer sufficient mechanical support for angiogenesis and tissue remodeling during wound healing, and also prevent the side effect of stress shielding. The bilayer composite matrix yield a higher percentage of the drug due to the higher absorption ability of the drug that the great efficiency of such system and give good achievement in wound healing application. So the last one is further investigation should be conducted upon the antibacterial test of the modified composite, since the bilayer composite is being mechanically locked within bromelain solution. So bilayer composite construct with antibacterial properties would be way forward. That's all from me. Thank you.